Today we are going to do section 6.7 on page 632 where we're going to do exponential growth or decay, which mostly we're going to base on this particular formula, okay? And then the E is number 2.7 something, right? And then T stands for time. A0 is the initial amount. So the growth or decay formula means if K is positive, then you have a growth situation. Your bacteria is growing like nuts. And then if it's a decaying, then your radioactive object is falling apart. Okay, and so let's look at the next page, page 633, where we have a graph of these two things. See, this is the growth one, right? You go, I think, let's see. No, I better. Which one is the growth one? Well, one of them is the growth one, and the other one is the decaying one. As time goes on, yeah, time is going that direction. So yeah, this is the growth one, and then the other one is as time goes on, it just fell down and passed out. So that is the two main models that we're going to be doing today. So let's look at example 1 on page. This is 633. Now, example 1 says a population of bacteria doubles every hour, and you started out with 10 bacteria, okay? You would think you start with more than that, but okay, we only have 10 bacteria in our little culture. And in this, the bacteria doubles every hour, and it started with 10, and then and we need to graph this thing. Now, it doesn't seem like we got a lot of information, but that's actually enough. Because what happens is that what we know is the bacteria doubles every hour. Okay, so let's see, it started with 10. We know that much, right? E. And then, so after 1 hour, so T equal to 1, we don't know what K is. K is some kind of a growth or decay rate. So, and then after 1 hour, we said 1 hour, the time is 1, then our bacteria has increased to 20. So with this equation, there's only one variable here, which is K, which means we can solve for K with the tricks that we've learned so far. So to do that, let's get rid of this 10, divide it over here. So we have 2 e to the power K, right? And T is just 1, so that has K left. And then to get rid of that, we will take the to isolate K, and here's a E here, we will take the natural log of both sides, because if you have this situation, let's see, which situation are we talking about? I believe this one, okay? If you take the natural log of E, B is E now, right? And then so log base E of E to the power X, log and B will cancel each other, so you have only X left. So that is the formula we're following. So let's slap natural log on both sides, okay? We have natural log 2 equal to natural log E to the power K, and natural log and E will cancel each other out to give just K. So K equal to natural log of 2, which is some kind of a number, and we don't know what it is, but it's something. Okay, so then now we can write down our formula, which is generally speaking, the formula of this bacterial growth will be A0, which is given as 10, and then e to the power K, which is natural log of 2. Okay, that's K times T, and that is how our bacteria grows, which means you just put the number, say 2 hours later, you put 2 in here, and punch this thing out, and that gives whatever amount that would be the amount of bacteria after 2 hours or after 5 hours or whatever you want to punch in here. This formula will give it. We can also plot this thing into the Desmos calculator or by hand if you like doing things the old-fashioned way. And then if you do, then you will come up with a graph like this. Okay, so here it is. Okay, here's what the book did, and the graph doesn't go past the You see the graph goes down here and stop here because this is, we start counting at 0, okay? Time equal to 0, so as time goes on, your bacteria is growing like crazy. So after 4 hours, you have something like 180 or so bacteria. And so that's example 1. Next, let's look at example 2. But before, yeah, example 2, okay? That is something about half-life. All right, so the word half-life, what it means is that this thing, after this amount of time, this thing will reduce by half, okay? And then, so let's do that. And let me write this down. All right, so now we are looking at, I forgot to write down example 2. All right, our example 2. Now this is, there's some object. Its half-life is 5730 years, okay? So then, so it started out at A0. The word 0 means that's the amount at time 0. Now, so it started out A0, and after 5730 years, it has become 1/2 of A0. Now, we don't know what A0 is because it depends on how much we're starting out with, but however much we're starting out with, this formula holds. Like say if you have 5 pounds here, then this will be 5 pounds times a half. If you have 10 pounds, that will be 10 pounds divided by 2, etc. So this formula just holds in for however much that you start out with. And then, what is the question? That is, we need to find this, the formula for this object, okay? And to do that, we need to figure out what k is. Now, in this formula, you notice we have 2 variables. Normally, we can't solve an equation that has 2 variables, okay? And because then you wouldn't, because normally what you do is you isolate one of the variable and kick everything else to the other side. But what if you have 2 variables? Then you have variables on both sides and you can't dig your way out, right? So, but however, in this case, the other variable is just sitting here and it appears equally on both sides. So we can cancel it out, see, in order to solve for k, because k is what we're looking for. The amount that we start with is not important, just whatever we start with. So to solve for k, which is sort of the decay rate, we will do the same thing as we done here, okay? So let's cancel A0 out because it conveniently is looks in such a way that it can be easily canceled. So then we have, pulling the same trick, we'll write down here, natural log 1/2 is going to be equal to, so natural log and e cancel each other out, so we only have this thing on top left, the whole thing, okay? 5730. So now we are in a much better shape because natural log of 1/2, whatever it is a number, okay, that we can punch out on the calculator. So this is just a number, and then this is another number. It's pretty big, but it's still just a number. We can punch that out in the calculator as well. And as a result, we can write down the answer for k. K is then this thing divided by this thing, right? It's natural log of 1/2 divided by 5730. And let's do that right now. Let's use our calculator and do this. It's a good calculator practice. Not that good. It's not very exciting, but let's do it anyway. Okay, I'll do it this way so you can see that formula that we're doing. So natural log, which has its own parentheses, okay, in my calculator, 1 divided by 2, close parentheses, equals. No, sorry, not equal. Go back. Let's see, divided. I forgot to do divided. Now I lost it. And let me erase this. Okay, I got it. So we have back to natural log 1 divided by 2, okay? And then I just need to divide by this number right here, and that'll give me k. So divided by 5730, that equals, it should equal to something. It equals to a very small number. Let me see. It refuses to change. All right, now this is what is this? The scientific notation or something? That is a negative number, and equals to, if we write it out, it will be equal to, so k equal to let's see, I'll write it up here. K equals to 0 minus, okay, 0.123. The 1 is in the fourth position, so 1, 1, 2, 3, 4. Yeah, and then there's a 2 here, and that should be right. Or we can just say, leave it in the scientific notation. Now the scientific notation, if you don't remember what it is much, it just means that you see it's 10 to the power minus 4. That means you need to move the decimal point to the right to make the one started out being here, okay? We have 1.2, okay? So then you move it 1, 2, 3, 4 locations, sorry, to the left. Whichever way then you move to make it smaller, okay? Because it's 10 to the power negative 4. That means it's much smaller. So let's move the decimal point so that it's much, much smaller. So this is a very small number. And that is, that is the decay rate of this chemical. Well, it makes sense because, like it says, it takes 5,000 some years for this thing to decay. So it's a rather slow going decay mode. Next, let's look at example 3 on page 636. We're still using this formula right here, okay? That is the growth or decay rate, doesn't matter, is A0e to the power kt. K is the rate of growth or decay. If its growth is positive, its decay is negative. So having said that, let's look at what does this want? It says a bone fragment is found that it contains 20% of its original carbon-14. So how old is it? So what we're going to do is the same as this one. Okay, let's write down this formula right here. That is, we have, however, at this time, we have only 20% of the original. So 20% is 0.2, okay? So 0.2 A0 is equal to A0. Let's write down the formula right here. E to the power K, KT. So T is what we're looking for. Now in this case, we just figured out in the previous problem what K is. K is this extremely small number right here. Okay, so right here, we know what K is. So we can just type that in, even though it is quite long to type. T is what we're looking for. But what about A0? We don't know what A0 is, but we don't care because it happens to appear in such a way that we can just get rid of it. So let's cancel out, okay? Just like the previous case. We'll cancel it out. And then remember, we know what K is in this case. K happens to be this thing because we're talking about the same object here, carbon-14 in both examples. So knowing that, then we're looking for T. All right, so then let's write this again. So 0.2 equals to e to the power, that thing, I'll write it down, 0.000121 t. All right, so we need to get rid of the e, right? And to do that, we'll slap the log in front. In the e's case, it's called the natural log. In this way, if you slap the log in front of e to the power something, then like this, okay, log in front of e to the power something, then that's something, then log and e cancel themselves out, and you have just that thing left. So we'll do that. So let's slap on natural log. This is the same thing we've been doing, okay? And we just keep doing this because there's nothing else to do here. This is about the only thing you do with growth or decay. So anyway, so that equals to 0.000121 t. Remember, this value, we got it from the previous example, is specific to, is the decay rate of carbon-14 that we got right here. Well, yeah. Anyway, so then that gives us t equal to this divided by this. So let's do that on the calculator, okay? And let's punch all these things in. Do not punch in the wrong number of zeros. Make sure we got the right number of zeros. And then that'll give us some kind of time, and we'll figure out what it is. So let's do that right now, okay? So let me see. Let's push clear. Oops. Anyway, okay, that looks okay. So we have, let's see, natural log what we're doing is, can you see it? Oh, there it is. Yeah, okay. What we're doing is natural log of 0.2, okay, over 0.000121. Yeah, so let's do that. Let's see, natural log of 0.2 divided by 0.123 zeros and then 121. All right, and then close parentheses. And does that look okay? And then equal, e equals something. What is that? Did I get it right? No, I typed it wrong. See, I have the natural log of 0.2, but I didn't have the close parentheses here, so that is wrong. Let's go back. I'll delete that. Back. Come on. Go back there. Okay, close parentheses divided by that. Okay, that looks much better. Push equal again, and now we have 0.2 divided by, oh, I'm missing the negative sign. That's why my answer is negative. Okay, let me add the negative sign here. So if I have the negative sign, that the answer would be positive. Is the 13,300 years, okay? And that is, let's see, that is what the book says, I think. Where is it? Yep. So the bone is 13,000 whatever years old. And that is example 3. All right, so next. Next, let's look at example 4, which is on the same page. Let me write that down. So next, example 4 on the same page, I believe, at the very bottom, it says that the doubling time of something, we don't care what it is, okay? The doubling time is 2 years. That's all we need to know. So we're following this formula again. So then doubling time is 2 years. So when so t equals 2, okay, we have the a0, the initial amount, and it got doubled. So we'll write down 2a0. It says so, doubled, right? And then e to the power k, and t is 2 years. So every 2 years, your object doubled, and we don't care what it is. So then we have okay. So then we'll do the same thing we did over here and before. Let's cancel out the a0 because we don't need it. And then, so we have that. Again, we'll take natural log to knock out the e, okay? So let's do natural log of 2 is equal to the natural log of e cancel themselves out. So we have only k times 2 left. So then k equals to natural log of 2 divided by 2. And then the equation of this thing, it says that we need, what do they want? It says we need the function, okay, not equation yet. Well, equation, whatever. The point is the amount, then the function to describe this thing would be y equal to a0 times e to the power k2, k being negative ln 2 divided by 2 times t. That should be the function. Okay. Now let's see what the book says. Yeah, that is what it says. It calls ya. All right. Now remember that in algebra, the word a0 and a are completely different variables. Okay, and that's the beginning amount. Well, though they do both represent a similar concept, but they are not the same thing. The a0 is the initial amount. A is the later amount, however much time that you want to go. So generally speaking, if you plug in the time here, then they'll give you the amount at that time. Say if you want to know 5 years later how much is in there, or 10 years later, and so on and so forth. Why do I have, what is that? Is that a negative sign? There shouldn't be a negative sign there, right? Because, yeah. Maybe it's equal. Well, whatever. There's nothing here. Okay. Let's get rid of that because k is natural log of 2 over 2, which I wrote down right here, times t, as our formula says. And that's about that. So next, we will look at something else. That is the Newton's law of cooling, which is very similar to this formula, except that the Newton's law of cooling has some kind of a initial, let's see, the temperature surrounding. Okay, there's one more object. There's a T of S in there. Otherwise, it's the same deal. So this will be the Newton's law of cooling, and that we will do next after I erase the board. So example 5, which is on page 638, we have we'll follow Newton's law of cooling, which is the same as the exponential growth or decay formula plus an extra number. Okay, this is the surrounding temperature. That's why it's called Ts. By the way, Sir Isaac Newton, if you didn't know that, is one of those great people in the history of mathematics and physics, where he invented calculus, right? And then the laws of motion, the 3 main laws of motion, and also various laws of thermodynamics, and then there's this here cooling, and I don't know what all. Okay, and just all out great. He came out with all this good stuff. So now we are going to look at this cheesecake, okay, and use it. We're going to use Newton's law to determine cheesecakes. Now a cheesecake is cooked to 165, and then it is put into a fridge. Don't ever do that, okay? Do not put a hot cheesecake in the fridge. You're going to ruin your fridge that way. Just leave it outside. But anyway, and these people who don't know any better stuck a burning hot cheesecake in the fridge. And so then after 10 minutes, the cheesecake has cooled to 150 degrees. So that's what we're going for. And by the way, this formula will rewrite this part as the temperature. The temperature, should we write a temperature? Nah, let's not write a temperature. We'll just keep it as Y. All right, so here's our formula. Then what we know right now is there are some things we know. Okay, in the beginning we have the time back when time was 0. Let's see, we have A, E. When k times 0, okay, time 0, that is when the cheesecake first got out and got stuck in the fridge. And plus the fridge temperature, which is its surrounding, okay, is 35 degrees. The time is 0. And then that is, that's the beginning. And then, right, then after 10 minutes, so this is the original situation. And then we've, now give me a second here. Well, I suppose it might be okay to call this thing T of T. You see, I was concerned that you might find that confusing to have 2 variables that has the same name. Okay, the small t means the time, the big T means the temperature. In English, they happen to be the same, start with the same letter. So then we have to put up with it. So try to remember that small t is time and the big T is temperature. So the temperature at certain time is what that is. Now, in that case, then this equals to, so the temperature at time 0 of the cheesecake is, as given, is 165. All right, so that is that's what we have. And the next piece of information we have is that after 10 minutes, okay, so we'll have A here, e to the k times 10. This number here is the time, right? And that equals, that went down to 150. And the surrounding temperature hasn't changed. Yeah, they're kidding themselves. If you stick a hot cheesecake in the fridge, that temperature is going to change very, very fast. But anyway, let's say that it doesn't, okay? A better example for this would be to say that it's freezing or nearly freezing outside, and you stuck the cheesecake outside on the porch to cool off. That would make much better sense, because outside is not going to be warmed up by your cheesecake. But your fridge most definitely will. Now, in any case, so then we have 2 equations. So we're going to solve for A from the first equation, and once we know what A is, then we'll be able to solve for K. So we have 2 variables that we need to dig out of. And the first equation is actually, there's a 0 on top. E to the 0 is 1. So the first equation becomes something much easier than it looks. It becomes 165 equal to a, okay, times 1, see, a times just 1, e to the 0, or anything to the 0 is 1. So then we have only this thing left. From there, we can get a then equal to 165 minus 35 is 130. All right, so we got a, which we can plug it in right here. Okay, in fact, I'll do it right now. Instead of a, we'll erase this thing and call it 130. Now, in that case, we can solve for k, which is our purpose here. Actually, I don't know if that's not actually our purpose, but solving for k will get us very close to what we're looking for. So let's solve for k. To solve for k, as we have been doing, what we're going to do is kick the 35 to the other side. Okay, that will give us become 150 minus 35. That should be 115, right? Yeah, and I hope so. And then the e is over here, right? And e of k times 10 is on top. This the 130 will push it down here, divided by 130. Okay, and then so the next thing we're gonna do is to say that the natural log of this thing. So ln of 115 divided by 130 is going to be equal to k times 10. So then 10 is, so then 10 is equal to this number divided by 10. So let's do that right this second, okay? After I find my calculator, let's do this, see if it's any good. Let's see, okay, I'll stand over here so you can see what we're doing here. So that's a fairly straightforward problem. We'll take natural log 115 divided by 130, right? 130, and close the parentheses, and then divided by 10. Divide by 10, 10, and that should be equal to something. That looks okay. It equals to negative 0.0123. Okay, that's what we will write down. So k, I'll write it over here. K equals to minus 0.012, and the last number I'll round it to be 3. All right, so but actually let me check to see if I got it right. I mean, I do mess up a lot, if you haven't noticed. Okay, in this case I didn't mess up. I'm okay. So k is this thing, all right, and what? So okay, we got k and we got a. What are we supposed to do here? We are supposed to figure out what happens when the temperature is 70 degrees. So, all right, so the question is, now the final temperature, see, T of time has to be 70. The final temperature has to be 70. We'll write this thing down again. Now we know A is 130 because we did that at some point, okay? And then e to the power k is that number, which I will write down, 0.0123. Okay, times t, okay? We don't know what time is it, but at some time that cheesecake is going to go down to 70, become 70 degrees, plus 35, okay? So the whole formula follows, and we need to figure out the number for t such that this number becomes 70. So we follow the same formula we did before. Okay, so let's do that. And then to do the same thing, we have to repeat what we just did, or we can just follow what we did before, which is let's not follow what we did before. We'll just redo this thing, because that is all we do around here. Okay, just solve this exact equation. And so it becomes 70 minus 35. That becomes 35, right? 35 divided by the 130, 130, and that would be, and then we take the natural log to get rid of the e, natural log, and that will be equal to what's on top, which is this thing, minus 0.0123. t. So if we solve this equation right here, then we can figure out what the time is. So let's do that. Take this thing, divide by this number, okay, to solve a t. So t equals, whatever that is, let's punch out on the calculator right this second. Okay, so we have, let's see, we have, let me clear this out. All right, we have the natural log, right? 35 divided by 130, close parentheses, and then divided by the negative. My calculator has a negative sign that's different from the minus sign. Yours might not be that way, okay? 0.0123. Is that right? Okay, that looks okay. Let's see what it says. Okay, I got 106, or something like that. About 107 what? Minutes or something, right? Let's see what the answer is. 106.68. Yep, that is what I have. See, that's what the book has, and that's what I have. And that should be the answer of this example. Yeah. So next we are going to look at something called logistic growth, which I will continue in the next video.